Hey, this is Math 8, in Unit 5, Lesson 12, and it's called How Much Will Fit? And so let's reason about the volume of different shapes today. So first of all, we're going to begin with two different containers, and we're going to say the small container holds 200 beans, and you want to estimate how much the large jar is going to hold in terms of beans. So here is the picture that is for you to take a look at here and talking about this one. And so if this smaller one holds 200 beans, the question is, how many beans would this one hold right there? So take a minute with your partner, of course, and try to estimate what you think this jar, how many beans this jar is going to hold. Okay? And so ways you might look at that, you might think that, well, this one here, if I kind of looked at that, maybe it's about this much in total. So maybe I can kind of divide this as 200, and then that would be 400 and 600 and 800 and maybe 1,000 beans. I mean, it's just an estimate, right? So it's about you talking through what do you think this container can hold, right? And so there's no super right or wrong answer. I mean, there would be if you had those containers. You could actually count the beans and see what it actually would be. All right, but the idea is for you to talk it through with what you think might be the case. I just look at that way and think this amount of beans, it's a little bit different shape. If I poured that in there, it feels like it'd be somewhere about here. And I might want to go 2, 4, 6, 8, and 10 and end up with 1,000 beans. That's just my estimate. That's my guess. You might have thought of something a little different, and that is just fine. Okay? So maybe you estimated it to be 1,000 beans. I don't know. Okay, next up we're going to look at some other containers. Okay, I'm going to get the iPad back out. And what we're going to look at the containers is it's going to tell you what how much one container can hold of something else. And then we want to use that same measurement as a way to compare with other boxes. So in the first one here, I'm going to move down to my pictures here, the next picture, moving down. Here we have a picture of some pasta, and we have some chicken culinary stock, and maybe it looks like some maybe vanilla pudding or something like that. All right, so if this box of pasta holds 8 cups of rice, how much rice would you need for the other rectangular prisms? So if this one here is 8 cups, we have to look at these ones and figure out, well, how much would they be if that one is equal to 8? Okay, and that's the idea. So if the middle box is 8, I'm gonna just draw a picture here of this one as 8. If that one's 8, I have over here this little pudding box, which is definitely not that same size. If anything, it might be 1/4 of that box. I could see how maybe if I cut this in half there and there, maybe 1/4. All right, so the box over here is maybe about 1/4 of 8. And 1/4 of 8 is 8/4, which is 2 cups of rice in the pudding box. Might be an estimate there. Now when it comes to the other box, this box of soup, the soup maybe is something like you cut that in half and maybe it's about half of that. So for the one over here, we might say that it's more like half of 8 cups, which is going to equal 4 cups in the soup container there. Again, I'm still just estimating, I don't know positively, but it looks like this one in the middle, or this one, this shape here, if that's 8, that shape here is about 1/4 of that size, and maybe that's half of that size. Again, it is just an estimate here. Let's take a look at the next picture. The next picture, I have a can of tuna, I have some rolled oats, like some oatmeal stuff, and over here I have organic pumpkin. So far I'm not feeling very hungry when I see these things there, but that's okay. If the pumpkin can holds 15 fluid ounces of rice, how much do the other cylinders hold? So they're all cylinders, and if this one is 15, the question is how much is in here and how much is in there? Well, the oat one, if we look at the oats, the question, if we look at that, this could either be maybe, again, you might think this is maybe twice as large. You might think it's 3 times as large. It's hard to say exactly. It definitely is a little bit wider than this one. So it's going to be more than double, okay? If we just doubled it, it would be the same diameter. So it's probably more than double, maybe closer to 3 times as much there. And so for the oats might be 3 times as much. Well, 3 times 15 is going to get you 45 ounces of fluid ounces of rice in the oat container. In terms of the tuna container, the tuna compared to the pumpkin is smaller, isn't it, right? And the tuna one is more like, it's probably the same size can. It looks like the same diameter. The tuna seems to be slicing probably more than half. Half is too much, maybe more like a fourth. Again, just an estimate. So tuna looks to be more like 1/4, or maybe we say it's, I don't know, let's just be nice. Let's go with 1/3 so we can have a nice number. So 1/3 of 15. Well, 1/3 of 15 is going to end up being 5 fluid ounces there, right? So that's just a way of estimating. It depends on what you want to say. If you wanted to say that it was more than a third, you might have a different answer there. I'm just going to call it a third because it works nice with the 15, honestly. Okay, and let's look at the next one. Here we have 2 ice cream cones. It says a small cone holds 2 fluid ounces of rice. How much does the large cone hold? So if that holds 2, we have to think about, well, how many of these, how much rice could I fill into this one? If that's a 2, how much is that one right there? And that's a difficult question. I would say, based upon what I know about ice cream cones, this is at least double, but probably more like 3 to 4 times as much. Hard to say exactly. Maybe not 4 times, maybe 3 times as much. If you were to double it, let's say it was 2 times larger. If it was 2 times larger, then it'd be 2 times 2, and you'd end up with 4 fluid ounces of rice. If it was 3 times larger, you do 3 times the 2 you began with, and it'd be about 6 fluid ounces of rice. It really depends upon how large you think that cone is and how much rice you think it's going to hold. Is it twice as large as the little one, or 3 times as large? It's up to you what you want to see there, okay? And finally, we have this one. It says, if a golf ball were hollow, it would hold 0.2 cups of water. If the baseball were hollow, how much would the sphere hold? So if this is 0.2 cups, this one is larger. But how much larger is it? Is it larger by just twice as much? Well, I think about it this way. This circle could fit here. I could put one there and one there, and I still have in my, what I can visually see, more space. I would say the baseball is probably 3 times larger than the golf ball in terms of the volume. Again, just an estimate. So if I multiply the 0.2 times 3 to make it 3 times larger, I would end up with 0.6, okay? And again, that's a maybe, 0.6 cups of water if I fill that up. I'm just estimating here, and so I'm not really doing some solid math. I'm just estimating what do I think this could be. And that's the idea behind these first kind of questions. Let's turn the page and look at the next side. It says, what shapes are the faces of each type of object shown here? For example, all 6 faces of a cube are squares. All right, well, in this shape here, back to the pudding picture, right? What are the faces on this one? Well, I have a rectangle shape here, a rectangle there, and that's still rectangular-ish. It's not fully square, but you could call it square. It really wouldn't matter too much there. Okay, here we have a circular face there, right? That's not a problem there. We have this curvy part that would go around it to make the cone part. For the cylinder, we know we have a circular base on the top and the bottom, and then we have a curved surface that goes around that. If you were to cut off that label, you would discover you have a long, skinny rectangle, but for now it's a curved surface there. And of course on this one here, are there any faces on a sphere? There are no flat sides, there's no faces. So we would say this seems to be more of a rectangle. Over here, we have a face that's a circle, and then we have maybe a curved surface as well. So we have 2 shapes there, a bunch of rectangles. Here we would have a circle on the top and the bottom, and we'd end up with another curved surface. My notes, I should number this. I'd have 2 circles here, 1 circle here. In terms of rectangles here, I'd have 6 rectangles there. All right, 1 curved surface, 1 curved surface. And here I would have just 1 curved surface, no faces on that one for the sphere. So which faces could be referred to as a base of the object? When we're talking about that base, you're talking about that flat part. So if you were to stand it up on a shelf or a table, what would it sit on? Okay, and so for A, for our first one, that's definitely going to be a rectangle. It's going to be the base that it's going to sit on. For the cone, we would say it's going to be a circle that it would sit on. Over here, for the cylinder, we would also say it's a circle. And for our sphere, we would say there's none. There's no base to a sphere. There's no flat side. If you put that down, it's just going to roll like a ball. And number 3, it says here's a method for quickly sketching a cylinder. It says go ahead and draw 2 ovals. Oval, oval. Connect the edges. Connect, connect. And there we go. So which parts of your drawing would be hidden behind the cylinder? Make these parts dashed lines. So practice sketching some cylinders, sketch a few and see what you got. So in terms of here, like this part here you wouldn't see, would you? Right? I would see the top of a can, for example, and I would pull that can down and I would see this side right here of the can, but I probably would not see that back side of the can over there. So I make that with a dashed line to indicate that it's not visible from what I can see there. All right, let's take a look at the summary for today. The summary today is just simply this, is that the volume of a 3-dimensional figure, like a jar or a room, is the amount of space the shape encloses. That's what volume is. Volume is the amount of space that something encloses. Okay, and we had some different shapes here, a cone, cylinder, a cube, and a sphere. All right, we could label those if you like. We have cone, cylinder, cube, and a sphere. And these are all 3-dimensional shapes, right? And that's because they have space inside of them we could fill with volume. All right, to help us see shapes better, we can use dotted lines to represent parts that we wouldn't be able to see if a solid physical object were in front of us. So we use dotted lines to show what is behind what we can't actually see. Let's take a moment to do our homework and then we'll check it off together. All right, first of all, here we go. Homework for tonight. Unit 5, Lesson 12, how much will fit? Sketch a cube and label its side lengths as 4 centimeters. This will be cube A. All right, so we're going to sketch a cube. To sketch a cube, we draw a square like that. And then I tend to draw a square. I start about the middle and draw a square like this to the middle point of that square. And then come over and then make it the same size. And then I connect the corners, connect the corners, connect the corners, and connect the corners. So if I wanted to make this properly, I'd have the dashed lines so you could tell what I could see and couldn't see. But we're going to make a side length of 4 centimeters, so I'll label this 4 centimeters right there. Now it says sketch a cube with side lengths that are twice as long as cube A and label its side lengths. Well, if that one was that long, I'm going to double that up. So let's double it up like this. Doubling it up, doubling it up, doubling it up. And then draw that again, same size. And connect my sides. And because I'm doubling it, if this one was 4, then this one's going to have a side length of 8 centimeters. I'm doubling the length there. Find the volumes of cube A and cube B. Volume is found by doing the sides cubed, right? Which is the same as a side times a side times a side. So for A, A is going to be 4 times 4 times 4, which is equal to 64 centimeters cubed. For B, it will be 8 times 8 times 8, which is equal to 512 centimeters cubed. Number 2. So several glass aquariums of various sizes are for sale at a pet shop. They are all shaped like rectangular prisms. Okay, so they're all shaped like this, aren't they? Something like that. That's what they all look like. Great, excellent. Okay, a 15-gallon tank is 24 by 12 by 12 inches tall. Match the dimensions of the other tanks with the volume of water they can each hold. Alright, so here's what we know. We know that when we take a tank that is a 24 by 12 by 12, we end up with a tank that happens to have 15 gallons in it. Alright, now let's multiply this together to find the volume of that tank. 24 times 12 times 12 is actually 3,456, and that's going to be inches cubed. Now that is what my volume is, and it holds 15 gallons of water. So what I know so far is that if I have a rectangular prism with these dimensions, I end up with a volume like that, and that volume holds 15 gallons. So now when I look at tank A, I notice that it's 36 by 18 by 12. I can find the volume of that by multiplying 36 by 18 by 12, and I come up with 7,776 inches cubed. That's larger than what I had over here. Now if that's 3,400 or so is 15 gallons, then 7,000 has to be more than 15, meaning it has to be either 20 or 30 gallons. But I can't tell quite yet, so I'm going to wait for now. Let's do the other ones. Here I have 16 by 8 by 10. When I multiply that out, I end up with 1,280 inches cubed. That is less than that one, so it's going to be over here in 1 or 2 are my choices there. Let's keep looking. Here I have 30 by 12 by 12, and 30 by 12 by 12 is 4,320 inches cubed. This number is also greater than 15 gallons, so it's going to have to be one of these. So most likely it's going to be, based upon this being 7,000 and that 4,000, it's probably going to be this one, but let's do one more problem. Here we have 20 times 10 times 12. And 20 times 10 times 12 is 2,400 inches cubed. Now with that information, it helps me out quite a bit because this is less than that, which means it's going to be one of these choices here. So now really I could put these in order from least to greatest. So my smallest value is 1,280. That's going to go with this tank here, tank number 1. So tank number 1, or 5 gallons is going to go with tank 2B. However you want to write this here. This one goes with that one. You can draw a line, whatever makes sense to you, right? The next smallest one at 10 gallons is going to go right here with D, 2,400. This is going to be tank number 2. So it's going to go with that one right there. Okay. Next we have the 4,300. So that's going to go with tank number 3. And then finally our largest one is going to go down here. So that's kind of your order for how this works. The 5 gallon one is tank 2. Right? You could write it this way, tank 2. The 10 gallon one is tank 4. The 20 gallon one is tank 3. And the 30 gallon one is tank 1. So depending on how you want to write that out there, that's what that looks like. Number 3. 2 paper drinking cups are shaped like cones. So paper drinking cup and paper drinking cup. The small cone holds 6 ounces of water. The large cone is 4/3 the height and 4/3 the diameter of the small cone. Which of these could be the amount of water the large cone holds? Now notice, it's a larger cone, right? It's a larger cone. How much? It's 4/3. Well, 4/3 is 1 1/3 larger. So it's going to be larger, which is important for us to realize, and that we're talking about the amount of water that it holds. Because we're talking about water that it holds, we know the first one holds 6 ounces of water. So let's take a look at my choices here. You might be thinking, oh, I don't know how to do this. You don't have to do math. We have to just do a little bit of reading, right? Look here. It's 8 centimeters volume. We're looking about ounces. Water's not measured in centimeters. Height might be. So right away, this one is not a choice. We're not measuring in centimeters. Neither are we measuring centimeters here. So I only really have 2 choices, 14 ounces or 4.5 ounces. Because this cone is 4/3 larger, and this one was already 6 ounces, it has to be greater than 6 ounces, which means there's only one choice, which is choice B, 14 ounces. That's the only one that has ounces, which is a volume, and is greater than 6 ounces right there. On the next one, it says, the graph represents the volume of a cylinder with a height equal to its radius. All right, so it's a cylinder, where the height is equal to its radius. So our radius here is like that, so I probably make this a little bit shorter like so. Okay, so height equals its radius, something like that. So when the diameter is 2, what is the radius of a cylinder? Well, that's the question about, do you remember what diameters and radius are, right? If the diameter is 2, that's all the way across, which is 2. And if that's the case, then what would be the radius? The radius is going to be half of that, so half of 2 is 1. Okay, that's our first one. Express the volume of a cube of side length S as an equation. Volume, we said, is equal to the sides cubed, or S times S times S. And so you can write volume equals S cubed and leave it just like that. Make a table for volume of the cube at S equals 0, S equals 1, 2, and 3. Remember, this is the volume of a cylinder, so we're not even looking at this graph right now, okay? So let's make one for volume of the cube with these side lengths. So I'm going to go ahead and write S. Okay, I'm going to write V for volume. There we are. So when my side length is 0, 0 times 0 times 0 is 0. That's fantastic news. My side length is 1. I get 1 times 1 times 1, which is 1. If my side length is 2, I end up with 2 times 2 times 2, which is 8. And if my side length is 3, I end up with 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So there's my volume for a cube. Remember, this is a cube one right here. Those are my volumes for a cube. So which volume is greater? The volume of a cube when S is 3. So there's my cube. When S is 3, the volume equals, what does it equal? 27. Or the volume of a cylinder. So cylinder when the diameter is 3. Well, for that, we just need to look at our chart right here. Here's the cylinder. And when the diameter is 3, what's our volume? We come up here, and we see it crosses the line right there at 11. So when the diameter of the cylinder is 3, the volume is 11. So which one is greater? The cube is going to be greater. Okay? And that's the idea. So you don't actually have to do any math there. Well, you do math for the cube, but then we use the chart to do the comparison there. Okay? All right, and finally number 5, our last one for today. It says select all the points that are on a line with slope 2 that also contains point 2, -1. So that says I have a graph that looks something like this. I know I have a slope of 2, and I know I have a point at 2, -1. That's going to be located right here. 1, 2, and 1. I have a point right there at 2, -1. That's what I know from what's given to me. Now because the slope is 2, I could continue to draw some lines here and plot some additional points, right? I could go up, because slope is 2, I could go up 2, which is going to go 1, 2, and over 1 to a point right here, which would be at 3, comma 1. Okay. I could also go down 2 and over 1 right here, which is going to be at a point at 1, comma negative 3. And I could do that again and go down 2 over 1, which is going to be at point 0, comma negative 5. Using these points here that we generated by knowing one point and the slope, I can write an equation for this line. It doesn't give me an equation, but I could certainly write one. The equation for that line is going to be y equals the slope times x, and then I put in where does it cross the y-intercept. That's going to be right here at minus 5. So y equals 2x minus 5 is my equation I want to use. So the question is then, all right, which one of these other points is going to be on that same line? Now already, without doing any work, I notice that A, 3, comma 1 is already on my little chart there. That's going to work just fine. I'll show you in just a second how to verify that. 1, 1, right, 1, comma 1 is here. Is that going to be on this line right there? Nope, no chance. How about 1, comma negative 3? 1, comma negative 3, it's one of our numbers. That's going to work no problem. How about 4, comma 0? Nope, not on a line, not going to work. And 6, comma 7, I don't know. I don't see it on there. So here's how we determine this. Again, we've done this before. We're going to take our equation, 2 times x. Our x value is 6. So we're going to say 6 minus 5, and we're going to solve that. 2 times 6 is 12 minus 5. 12 minus 5 is 7. Does that match our y value? Yes, it does. And since it does, that is going to be another point on that line. We would do this same process to verify A and C as well. All right, so that's what we do for number 5. And we have one more, number 6, to solve. And here we have two equations, y equals negative 2x minus 20 and y equals x plus 4. So what we want to do is set them equal to each other. We'll say negative 2x minus 20 equals y. Well, what does y equal? Y equals x plus 4. So now let's go ahead and add 2x here, add 2x there for a total of 3x. Let's subtract 4. Subtract 4 for a negative 24 equals 3x. Divide both sides by 3. And we have negative 8 equals x. There's our x value first of all. Now we need to find a y value. So we take this number and we use our equation to plug it into any one we want. I'll do the smaller one.